Okay, good morning. So in last class, I had given you these two problems. Okay, so for that you were required to calculate the shape force and bending moment and draw the shape force and bending moment diagram. Right. First case is a simply supported beam with a concentrated load at the midspan, and the second case was a simply supported beam carrying concentrated load anywhere on the span. Okay, the position may be anywhere over here. So let's go ahead over this. I'll take up this second case wherein the load is positioned somewhere within the span. It may not be exactly at the center over here. So these distances, they are A and B. Okay. So the position of the load is at a distance A from support A. Okay. And if you measure it from support B, it is at a distance B over here. And the total span is L, which is equal to A plus B. So in this case, if you determine the reactions VA, so VA comes out to be W into B by L, okay? And VB will be equal to W into A by L, okay? That is by considering the equilibrium of the entire beam. This is the reaction what you'll be getting over here. Now, after this, so what we have is, if you have calculated the reactions, uh, can you tell me, can confirm these are the reactions what you'll get? Yes, I hope you have got the same reaction if you have tried solving this. So now shear force in this beam, if you try determining that, first we'll start with point A. At point A, this shear force will come out to be VA, which is equal to W into B by L. So W into this B upon L, which will be equal to RA or VA at this point. Now, next is, if I take this to be point C, I'll go to point C. So here the shear force will be equal to VA. If I take a section over here before crossing this concentrated load, okay. So VA, so that is VA itself, which is equal to W into B by L over here, okay. So next is shear force to the right of point C. This is before I cross the concentrated load, okay. So in this case, that will come out to be VA minus W, okay. So this will be W into B upon L minus W over here, okay. So you can further write it as B by L minus 1, okay. Or what you have is minus W into A by L. That should be the value over here, because B minus L will come out to be minus A, okay. So this will give you minus W into A by L. Shear force once you cross this point C, the concentrated load at point C. When you cross that one, this is the value what you'll get. Before crossing the concentrated load, the shear force will be W into B by L. Similarly, shear force at B, okay, so that will come out to be W minus W into A by L. Okay, before I cross this support reaction, it will be minus W into A by L, because it will be sum of all the forces to the left of my section. So on the left side of my section, I have VA and this W. Okay, so I can even write it as to the left of support B. This will be VA minus W, which comes out as minus W into A by L. And when you go to the right side, right of support B, so that will come out to be VA minus W plus VB. Now VB will come in. Okay, so that will be W into B by L minus W plus W into A by L. So totally this will come out to be 0 when you add up, because this is W into A plus B by L. A plus B is nothing but L over here. Okay, so it will be plus W minus W, which will be 0 over here. Okay, so this is the value of shear force in this beam. Now moving ahead with the bending moment values for calculation of bending moment. So at point A, you will have bending moment as 0. You can say point A or support A also. The bending moment will be equal to 0 here. Okay. Now we'll go for point C. So at point C, what is the bending moment value here? It will be equal to VA into A. Okay. If you take the section, all right. So if I take a section exactly at point C, right over here, what are the forces to the left of the section? Only this VA. What is the moment due to this force? VA into this distance A. Okay, VA into A. So I'll be having bending moment as VA into A. So this will come out to be VA is W into B by L. So that into A. Or you can say the bending moment at point C will be equal to W into AB by L. W into A into B by L. Okay. And later at bending moment at point C, sorry, it is support B. So that will reduce to 0. Even by calculation also, this should come to 0. Okay. So you can try calculating that. It has to come to 0. And if you check, this will be the maximum bending moment in this beam. Now, how the shear force and bending moment variation will be there? So that is, we'll plot the shear force and bending moment diagrams over here. So this is the beam we have. Okay. And this one is for bending moment. Okay. Now first is we'll go for plotting the shear force. At point A, the shear force value what we had, this is A over here, and B, whereas this is point C somewhere here. Okay. So A, B, and C. And since this beam is carrying the concentrated load, the variation, okay, in the shear force will be constant. I'll show you in this diagram over here. C and B. Okay. So first is this shear force diagram. So shear force at A, it was W into B by L. At point C, it was W into B by L before I crossed that concentrated load. Once I had crossed the concentrated load, it is coming out to be minus W into A by L, which is remaining constant till point B. And once I cross the support B, it is coming to 0 over here. So that is how the shear force is varying in this beam. So for that purpose, what we have is, so this is W into B by L, okay? And it will be constant till point C. So no change in this value up to point C. Once I cross the concentrated load at point C, it is coming out to be minus W into A by L, okay? And thereafter, again, it is remaining constant up to this support P till I cross the reaction at support P. After I cross the reaction at support P, it is coming back to 0 over here. Exactly at point B, it will come out to be 0. Okay, so this is the variation what we have in the shear force, or this is the shear force diagram over here. And in this portion, AC, the shear force is positive, W into B by L plus W into B by L. Whereas in portion CB, once you cross that concentrated load, the shear force is having a negative value of minus W into A by L. So this will be our positive shear force and the negative shear force. It indicates the nature of the shear force, how the shear force is varying. Okay, so this is the shear force diagram. And next for bending moment diagram. Okay, so here what is happening at point A, bending moment is 0. So if I write, this is W into B by L, W into B by L, and W into A by L, W into A by L. Shear force values for bending moment. Okay, so at point A and B, bending moment is 0. Okay, and at point C, it is W into AB by L, what we have calculated here. Okay, W into AB by L. So I'll have an ordinate at point C, okay, equal to W into AB by L, representing this value of W into AB by L over here. Okay, so this is the ordinate at point C. And then how is the variation? In case of concentrated load, the bending moment will be varying linearly like this. From 0, it will increase to W into AB by L. And again, from this point onwards, it will start reducing to 0, from W into AB by L to 0 over here. Okay, so this is the bending moment diagram for that beam. So entire bending moment is positive. We have the whole beam under sagging. So this is positive. What is the value over here? This is maximum bending moment is W into A into B by L. Okay, you can check it. You'll get this itself as the maximum bending moment. Here itself, the shear force is changing from positive to negative. So at this point C itself, the shear force is crossing that 0 value, right? So what we have is, this is the maximum bending moment over here. Okay, you'll not come across any point of contraflexion in simply supported beams. You'll have point of contraflexion in overhang beams over there, and when you have come across couples applied in the beams, in such cases, you'll come across the point of contraflexion. In this beam, we don't have any point of contraflexion over here. So this is the bending moment value, right? And I had given you for the first case. In first case, what you have is That is in the first problem what I have given. A and B, they are equal, which are equal to L by 2. Okay. Even you can use this equation for that also. If you substitute A and B equal to L by 2, you should be getting the value of shear force and bending moment also. So that's why I took directly the second one. So even the simply supported beam carrying a concentrated load at the midspan, okay, you will have A equal to B equal to L by 2 in that case also. So if you have calculated that, if you substitute these A and B as L by 2, both A and B as L by 2, you should be getting the shear force value as W by 2 over here, okay, minus W by 2, minus W by 2. Okay, that should be the value. Exactly at the center, under the load, the shear force is changing the sign. And maximum bending moment in that case will be WL by 4. Okay, in that case, the value of bending moment in that case, when the load is applied exactly at the center. So maximum bending moment will occur at the middle of the span and its value will be WL by 4. All right. Is that clear? So another case of loading, what we have is a uniformly varying load, UVL. We have dealt with UDL, simply supported beam carrying UDL, simply supported beam carrying a concentrated load at the mid of the span and somewhere within the span that we have taken up. The next one will be about the uniformly varying load. Okay, when you have a uniformly varying load applied on the beam. So we'll be having something like this, a uniformly varying load. So it will be changing from 0 to some maximum value. Okay, so this is how the variation in the uniformly varying load will occur. So let us say at this point it is W per unit length. Okay, so this will be acting like this in a downward direction throughout the beam. So this is simply supported beam supporting the uniformly varying load throughout its length or throughout its span. Let's say span is L. And we'll take this as A and B points, two supports. Okay, now we need to calculate the shear force and bending moment in this case. So here, first is support reactions. What we have is, if I take this to be VA, vertical reaction at A, and this is VB, vertical reaction at B, you may also call them as RA, RB also. So first condition of equilibrium says summation of forces in vertical direction should be 0 for maintaining equilibrium. If I apply it to my beam, it tells me VA, okay, plus VB, which are in upward direction. I've taken them positive. And uniformly varying load, it is acting in a downward direction. So its total load, okay, this is spread over a length L. So if you want to know what is the total magnitude of this load, the resultant of this uniformly varying load, you need to find the area of this triangle. Area of this triangle formed by this uniformly varying load. Okay, so here the height of the triangle is W per unit length. This intensity itself represents the height of the triangle, and the base is L. It is spread for a length of L units. Okay, so what will be the total load? It will be area of this triangle, half into L, the base, into W, the intensity, height, which will be the height of our triangle. So that should come out to 0. Or we can further simplify this as VA plus VB will be equal to W into into L by 2. Okay, so that will be VA plus VB will be equal to W into L by 2. Now next what I have is one more condition of equilibrium is summation of moments should be equal to 0. Okay, so for convenience in such cases, if I take moment about this point, okay, about this side of the triangle, it will be simple for me to calculate the reactions. Okay, it might be done by taking about the other point also, about this point B also, where the intensity is 0. Okay, so I'll take moment about point A over here, right? So when I take summation of moments of all forces about point A and equate them to 0, what do I get here? So I'll take moment of this VB over here first. So VB, it is having a anti-clockwise moment about point A. This VB will have a anti-clockwise movement. It will try to rotate the beam in anti-clockwise direction, this force, this reaction. Okay, so for that purpose, minus what is the distance I have to multiply for getting the moment? This is L. From point A, it is at a distance of L over here. So VB into L minus VB into L because it is anti-clockwise. Then this uniformly varying load, okay, so what happens is it will be having a resultant over here. So it will be acting somewhere at this point. This is our resultant of this uniformly varying load over here. So what will be its resultant? We have already calculated that it will be area of this triangle. Okay, so that will be half base into height. Okay, so that resultant magnitude is WL by 2. Now question is at what distance it will act. Now if you have studied the CG and MI, there you have calculated the CG of a triangle. So it will be at a distance of L by 3 from this end. Okay, this distance will be L by 3 over here. 1/3 of this base from this end, whereas from the other end it will be 2L by 3. This will give us the location of the resultant where it will be applied. Okay, it will be exactly at the centroid of this triangle. It will act exactly at the CG of this triangle over here, which is at a distance of L by 3 from A or 2L by 3 from B. Okay, now I can take moment of this force. So this total magnitude is WL by 2, magnitude of this resultant. Okay, so what will be the moment about point A of this UVL? It will be minus, plus, because it is clockwise, WL by 2 into the distance. At what distance it is acting? L by 3 into L by 3 over here. Okay, so this is the movement of all forces about point A. One movement was due to VB, the reaction at B, which is minus VB into L, anti-clockwise movement. The other force which was having movement about point A is this uniformly varying load. In that case, we have first determined the resultant of this uniformly varying load, and then we have calculated the moment of that about point A, okay, which will be this WL by 2 into the distance L by 3. Okay, so this summation should come out to 0 for equilibrium, or this will tell us what is VB equal to minus VB into L plus W L square by 6 should be equal to 0. Or what VB will be equal to in that case? VB will be equal to W L by 6. Okay, if you substitute this value in the first equation, what we have here, okay, in this one, right? So if you substitute the value of VB in this one, then you'll get to know what is VA equal to. VA will be equal to WL by 2 minus WL by 6, or VA will come out to be how much? WL by 3, okay, Is that fine? Please tell me, calculation will be coming out to this values or no? Or if you have any doubts, you can tell me. First thing is reaction should be correct. You should get the correct reactions. Okay. Then we can go ahead with calculation of shear force and bending moment. See, you should be having VA as WL by 3 and VB as WL by 6. If that is the case, then we can go with this calculation of shear force and bending moment further. Then what we have in that case here, so this is the beam what we have taken, and VA and VB are determined. Then what we'll do is we'll start considering a section. So first is I'll take a section over here at A, directly at A. Before I cross A, I know that shear force value is 0. So once I cross that support reaction, the value, what will happen to the value over here? So this is our section. So taking sum of forces to the left of section, shear force calculation over here. I'll take at support A, it will be equal to VA. So VA is on the left side of the section and it is an upward force. So because of that, we have positive sign for that. So this will be equal to WL by 3 over here, VA value. Okay. Then at support B, since I don't have any point in between the beam, I'll go to support B itself directly. So at support B, it will be equal to what? VA minus this total load, all this uniformly varying load, which will be equal to half into base L into W, the intensity, height of the angle. So that will come out to W into L by 6 over here. If you calculate that, you'll see that it will be equal to W into L by 6. This is the shear force at B. Once you cross that support B, it will be 0 because you will be taking in this VB reaction. So to right of support B, the shear force will be equal to VA minus W into L by 2 because of that uniformly varying load plus VB. Okay, so if you substitute the values, you'll get it as 0, WL by 3, okay, minus WL by 2 plus WL by 6 over here. So this ultimately comes to 0. Okay, these are the shear force values what we have. Okay, now the bending moment values, calculation of bending moment. Okay, so here at A, you have the bending moment as 0. The bending moment value will be 0 at this support A over here. Okay, take the forces to the left of this A. There are no forces to the left of A, so there is no bending moment. That will come out to be 0. Bending moment at point B, if we calculate that, so that should also come out to be 0. So what we have, if I take left side forces, when I come to point B, okay, when I take this support to this point B, now if I consider all the forces to the left of the section and take their moment about point B, what happens in that case? So it will be VA into L. Okay, this will have a clockwise moment. So as per our sign convention, left side clockwise movement, we'll consider that to be positive, okay? And other sign convention, if at all, if the left side movement is anti-clockwise, left side means to the left of my section, if the movement is anti-clockwise, that I'll take it as negative. So VA will have a clockwise movement about point B. When my section is at B, VA will have a clockwise movement and it is to the left of my section, okay? So this will be positive. So plus VA into L, and UL, this UL will have anti-clockwise movement. So from that it is negative, minus this total load W into L by 2, okay, into, what is the distance now? 2L by 3. I am taking moment about this point V, so I will multiply this 2L by 3 into 2L by 3, okay. So this is W into L by 3 into L minus W into this 2 and 2 is gone, L square upon 3. You can see W square by 3, W square by 3. So this moment will come to 0. Okay. So this is my calculation, what I have. But other than this, what I require is somewhere the bending moment will be maximum over here because of this one load. We need to find where the bending moment is maximum. Okay. So clearly, I don't know where my shear force is changing the sign. Okay. We had calculated the shear force. So I have not considered any point within the span over here. Okay, I have not taken any point within the span of this beam. Okay, somewhere in the middle, I have not taken any point. I'll directly calculate shear force at A, the shear force at B, and I have written the values over there. Now these two are indicating the only the positive values. I don't know where the shear force is 0. Okay, so let us try finding that one. Somewhere within the span, shear force will be changing the sign. So what will happen in that case? Shear force at A and B. Okay, I think this will be negative, correct? I have not taken the correct sign over here. I take WL by 3. So this is WL by 6 minus WL by 2. So this should come out to be negative. Yes. So I only know that it is changing from positive to negative somewhere within the span. So where the shear force is 0. Okay. So we'll first determine that distance where shear force has become 0 over here. Okay, then we'll find the bending moment at that point. So what I'm calculating now is maximum bending moment. So maximum bending moment has to be calculated. So what we have for bending moment to be maximum, we have written these conditions before also. We have dm by dx to be equal to 0, or in other words, what we can say is dm by dx is nothing but it is equal to shear force at the point. Okay, so that should come out to 0. Shear force should be 0. Anybody with difficulty or doubt over here? So what I'll do is I'll go for taking this condition. Shear force should be 0 for the bending moment to be maximum. Okay, so what is the value of shear force, or what is the point or distance where our shear force is coming out to be 0? Let us say we have the 0 shear force somewhere at a distance x over here from point A. I'll consider the section at a distance x from point A. And let us say at this point the shear force is becoming 0. What is this like x value now? We have to find that one. So what is the sum of all the forces to the left of the section that has to be taken? Okay, then we can equate it to 0. So what we have to the left of the section, this is the loading part. Okay, what is there? So for calculating the shear force, I can even take sum of forces to the right of the section also. It may be to the left or right. Okay. So what is the shear force we have defined? It is a algebraic sum of all the forces either to the left or right of the section. Okay. Now, if you want to save your time and with uh, quick calculation, if you want to proceed, it will be simple if I take summation of all the forces to the right side of my section. Okay, if I consider all the forces which are to the right of the section. Okay, both will give us the same value, whether you takes algebraic sum of forces to the left of section or to the right of section. At this particular section, shear force will be having only one value. Whether you calculate by taking the summation of forces to the left of section or to the right of section, it should be coming out to be same. Okay, until now what we have followed is we have always taken sum of all the forces to the left side of the section. Okay, so that was the procedure what we have followed. Now we are here in this particular case for this problem. Here in this we'll change it slightly. Okay, for convenience we'll go for taking summation of forces to the right side of section. Okay, so what we have is sign convention for shear force. This is the positive shear force, and this is our sign convention for negative shear force. Okay, please keep this sign convention in your mind. Okay, so this is the sign conventions that we are following. Okay, now what I'm doing is I'm finding the point of zero shear force. Okay, where is my point of zero shear force that I'm determining over here? Okay, so for that, what I'm taking is I'm going to consider summation of forces to the right of my section. This is my section over here. I will take algebraic sum of all the forces to the right side of this section. Okay, so in this right side, whatever the forces are there, so that we are going to take, and we'll find that point of zero shear force. So that will be more convenient for me to solve this problem. That's why I am taking to the right side of the section. Okay, summation of all the forces to the right of section. Is that fine? What I said, is it clear to you? Now, section is over here at a distance x from me, or I can say it is at a distance L minus x from point B. Okay, so this is the section. Now what I'll do is I'll take all the forces to the right side of this section here and apply proper sign convention. So let us see how we get the this one shear force value over here. Shear force at a distance if anything is not clear in this part, please ask me, unmute yourself and ask me. I want to find maximum moment. For that, first thing what we have to do is find the point where shear force is zero. Okay, so this will be the position of our section. Either it is at a distance x from A, or even you can say it is at a distance L minus x from B. Okay, so now what we'll do is taking the sum of I'll take the sum of all the forces to the right of my section. Okay, to the right side of my section. So in that case, what will happen is I want this beam, this diagram for me. So I'll keep it over here. Now we'll take that summation of forces. Okay, so shear force at a distance of L minus x. Okay, L minus x from B. What will happen to the shear force at the distance of L minus x from B? So I'm considering the summation of forces over here. Summation of forces to the right of the section. I'll follow the sign convention, what we have taken. So what are the forces to the right side of section? We have VB. Okay, so this will be equal to VB. Okay, so what I have, right side upward force, it should be negative. I should assign a negative sign. So it will be minus VB as per our sign convention. Right side upward force will be taken to be negative. Then what is the uh, UVL present on this portion, on this L minus X over here, this part. So what is the height of the triangle at this junction? So that we need to determine. So it will be W by L into L minus X. From similar triangle, you'll have to find it out. Okay. So intensity over here at this point, it will be W by L into L minus X. Okay, over here, the intensity of UDL will be W by L into L minus X over here, right? So what will be the total resultant of this UVL, what is present over here? It will be area of this triangle, okay? Area of this triangle which is present on this L minus X, okay? So the height of this triangle we determined it is W by L into L minus X. Base of the triangle is L minus X. So minus half into base L minus X into height is W by L into L minus X over here. Okay, so this is what the shear force is at this section. Okay, over here. This is my section what I have taken at this section 1 1. So if I substitute for VB, it is minus W L by 6 over here. Okay, and what it comes out in this bracket, what I have, you can calculate along with me, solve this equation. Okay, so this will be W by 2L. Okay, this will come out to be L minus X the whole square, L square plus X square minus 2LX. Okay, so this is what the equation will be. So finally, for maximum bending moment, we need to have for the shear force to be equal to 0. This equation should come out to 0 here. Okay, or I can write minus W into L by 6. Okay, minus W into L by 2. If I open up this bracket and multiply the terms, minus W into L square, L minus W into L by 2 into X square, W by 2L, WL square by, only W, wait a minute, let me correct this. It will be W by 2L into X square, and this one will be plus W into X. Okay, this is a simplification of the equation. So this should be equal to 0. Okay, so what happens over here? I can take this WL, okay, WL by 2 and this WL by 6. What it comes out? Minus, can anyone give me what will be this? Minus WL by 6 and minus WL by 2. Minus 4 WL by 6 or it will be minus 2 WL by 3. Is that okay? Minus this will be W by 2L into x square, okay, plus W into x should be 0. So you need to find the solution for this equation. It will tell you what is the value of x. That will be the point where shear force will be 0 or the bending moment will be maximum. We need to solve this quadratic equation. So you need to get what is the value of x. So you can find that by getting the roots of this equation. Okay. In this case, A is a W by 2L. B is minus W, whereas C is 2WL by 3. Okay. So substitute these and find what will be the value of x here, positive value of x. Okay, so solve this one, solve this equation and tell me what will be x. Substitute for A, B and C in that one. See what you will get the value of x for that.
Hello, sir.
Yes.
So in the first term, the second equation should be plus or minus, sir. So because it is on the right side, so
Mm-hmm. Okay.
in the first equation,
Second,
minus VB.
minus VB. This should be plus, correct. Right side, downward force, positive. So what should change here? This sign should change and these signs will be reversing. This will be negative. Okay, that will be the sign change. So this is minus, and in this case also, what will happen to the signs, this values and signs? Correct. This value will change plus wx square, and this is minus. This is minus. This will be minus w by 6. So that will be equal to 2 by 6 or 1 by 3, WL by 3. So this will be WL by 3. And here also it will be WL by 3. C will be equal to WL by 3. Check it now. So if you solve, simplify that, you'll get x as 0.577 times L. Okay, this is the point where shear force will be 0. Okay, and on substituting for this bending moment, if you find maximum bending moment over here, okay, or bending moment at a value of x equal to 0.577 L, so that will come out to be, try this one, solving this one, what will be that value. So again, I'll take moment of all the forces on the right side of section. So it will be, this is right side anti-clockwise movement, so negative, sorry, it is positive VB into L minus X, okay, and minus, this is W by L
So we can't hear you.
okay. Now the maximum bending moment value what we have is, okay, you get it in terms of equation, it is better than that. Just keep it in the form of equation only. Okay, taking moment of all the forces to the right of section. Okay, you need to calculate that maximum value of bending moment. Please put your attendance in the chat box till we finish this one. So maximum bending moment here will be VB into L minus X. Okay, so this is plus minus, this will be area of that triangle, which is half into W by L into L minus X. Okay, and the distance will be L minus X by 3 from our section. Like we did it for the entire beam, now we have to consider only this part of the uniformly varying load. Okay, so if you solve for this on substituting the value of X in this and solve it, you'll get to know what is the maximum bending moment value. Okay, so you try that one, we'll see how much will, how many of you will get that value. This will be having a variation something like this. Variation of shear force diagram. It will be varying quadratic. The variation in the shear force will be quadratic because if you look at the shear force equation, what we have written, it is having x square terms. If you write it for that shear force, we are not written for that actually, but in case of uniformly varying load, okay, so the shear force will be varying in a quadratic manner. So you get to know this point where shear force is 0. That is x over there. Okay. So here in this case, we are coming across variation of shear force in a quadratic manner. Okay. So this will be the shear force diagram. Okay. And in case of bending moment diagram, the bending moment varies cubically. We don't have to plot any cubic curve itself exactly, but the variation equation says that the variation will be in a cubic form. So that will be represented by a curved line. Okay, the maximum minimum value will be exactly below this point of zero shear force. Okay, try plotting this. I have given you a rough idea of bending moment diagram and shear force diagram. Once you get this value of x, confirm what will be value of x first. Okay, correct me if it is anything else, and then go for getting the bending moment value, calculating the bending moment. Okay, right. So these are some standard cases what we are taken. You may be asked to obtain these equations also. So we'll stop at this point. You can exit from the meeting.